Today we're going to talk about section 9.2, sums of arithmetic sequences. There are some special tricks that work only for arithmetic sequences. The things we're going to do today only work if a sequence is arithmetic. But they're so cool you will want to use them all the time. Don't. So let's start with add the natural numbers from 1 through 50. So the natural numbers are 1 plus 2 plus 3 plus 4 plus 46 plus 47 plus 48 plus 49 plus 50. Okay, well, if we started at the start and we did 1 plus 2 is 3 plus 3 is 6 plus 4 is 10, we would be working at this for a while. But if we take a tip from Carl Gauss, who was the first person to see this, if we add 1 and 50, we get 51. And if we add 2 and 49, we get 51. And if we add 3 and 58, we get 51. This is going to keep happening because it's an arithmetic sequence. We're adding the same thing to each term. So as this term gains 1, this term actually lost 1. So we're ending up with the same sum. Well, that would be, if there are 50 numbers, then there are 25 pairs of numbers that each add up to 51. So simpler than adding all the numbers from 1 to 50, we could just do 51 times 25, which is 1,275, either by a bit of quick work on the side or some calculator work. So let's try that again. Let's try that for the sum of the terms of 7n minus 4 if we're looking at the terms from the first term through the 40th term. Well, the first term is 3, and the next term is 7 times 2, 14, minus 4, 10. And the third term is 21 minus 4, 17. And we would keep going. The 39th term is 269. And the 40th term is 276. This is an arithmetic sequence that looks linear. And if we try Carl Gauss's trick, 3 plus 276 is 279. 10 plus 269 is 279. Indeed, it's happening. These terms are going up by 7. These terms are coming down by 7. So we're going to get a common sum of 279. And we would have listed 40 numbers, 40 terms. So there are 20 pairs of 279, which is 5,580. So we have our sum. Okay, suppose we want the first 200 terms of the sequence that's defined by 1/2 n plus 4. We want to add them all together. Well, since this is arithmetic, I know I'm going to need the first term, which would be 4.5. The second, well, I don't necessarily need the second term if I realize that somehow in here we're going to get a lot of terms. The 200th term is 104. That sum that I'm going to get is 108.5. And if I have 200 terms, then I will have 100 pairs, and that makes 10,000 850. So let's take a look at this in some generality, right? So let's actually create a form. So what we were looking at was the first term and we paired it with the last term, which at this point we'll call a sub n, the last term that we use. And we added those together. And we could see that the second term and the second to last term made the same sum, and the third term and the third to last term made the same sum. And so we multiplied this by the number of pairs of terms, which the number of pairs of terms is 1/2 the number of terms. So some people do this as a sub 1 plus a sub n times n divided by 2. This would be the sum of the first n terms of an arithmetic sequence. Okay, so let's take a look at another example. Suppose it came to me in this form, 2, 5, 8, 11, and I want the sum of the first 32 terms. Well, first let me check to see if it's arithmetic. We're adding 3, we're adding 3, we're adding 3. It is arithmetic. So this would be, the functional formula for this would be 3n minus 1. So the 32nd term would be 3 times 32 minus 1, 96 minus 1, 95. So the first term, 2, plus the last term, 95. That makes 97. And then I had 32 terms, so I will have 16 pairs. And 97 times 16 is 1,552. So that would be the sum. Notice that when the problem came to me this way, and they asked for a sum, I had to generate the functional definition so that I could find the last term so that I could then run my process. So here's another one. Add 6, add 6, add 6. So it is arithmetic. In fact, it's 6n plus 5. Okay, so 6 times 1 plus 5 would be 11. Okay. And then I need the 7th term. Oh, wait a minute. That feels kind of awkward to me. Let's run it, and then we'll double back to see. Well, first of all, let's cope with this. Because if we have an odd number of terms, we don't have an exact number of pairs, right? Because if it's 7 terms, it's 3 pairs, and then there's somebody left over without a partner. So let's actually run this. Let's list them all and actually see what happens. 23 plus 29 plus 35 plus 41. That's it. 1, 2, 3, 4, 5, 6. I need one more term. Plus 47. Okay. So this makes 58. And this makes 58. And this makes 58. And the guy without a partner is half of 58. So we have 3 full pairs and half a pair. So the sum here, 3 times 58 plus my 29 is 203. So let's run it this way. Let's see if I'm going to switch colors. All right, so our functional definition, 6n plus 5. So our 7th term would be 42 plus 5, 47. That's good. We do our first term, 11, plus 47. That's 58 times half the number of terms, so 3.5. So 58 times 3.5. I'm going to punch it up on my calculator just to make sure. 58 times 3.5 is 203. So it works. So even if the number of terms is odd, our formula for finding the sum still works.